Okay. So Todd is going to talk about the power aspect, power distribution system. He puts a great presentation, guys, about the difference between, I always get confused between remote centers and panel boards and switch gears and switch boards and a bunch of other things. And he also does a really nice overview of the power system. So great presentation. I know Adam, you're in touch with him. You need something. He's in touch with him. Adam is already in touch with him for one of his projects. So you guys want to see Todd a lot in the electrical industry. So with that, go ahead and start.
Thanks, Chad. Yeah, just a little bit about myself. Todd Christensen. I was actually born and raised here in the cities. I was hired by Eaton Corporation in '94, and then spent some time, about 10 years, in Chicago in that area doing some various roles, sales engineer, project manager, etc. Before I came back up here about 10 years ago. My role up here in Minneapolis is that of application engineer. Application engineer is it's kind of a hybrid role, but what I primarily do is work with consulting engineers and users and design build contractors to assist them with uh, the manufacturer's product and availability to meet their design needs. So from a manufacturer standpoint, there's really four major manufacturers that you may have run into. There's Eaton, Square D, Siemens, and Schneider are pretty much the four major electrical distribution equipment manufacturers for North America right here. Um, from an equipment manufacturer standpoint, there's a lot of times where there's concepts that come on paper, or somebody says, here's what I want to do, but I don't know how to do it. And I take that concept and kind of roll it into an actual product. And sometimes there's new products where it's my job to kind of say, here's something new in the market, never existed before, put it in your basket of tricks. So when you're sitting down doing stuff on paper, whether it's space savings, cost savings, or whatever the goal of your project is, uh, my job is to make sure the products are available to fit your goal. So I think Adam, is that my shot? Or you guys, anybody else been in the industry before or in the future, contractor or engineer?
Actually, I did his job.
Have my shot? Okay.
Yeah, I started the project. So.
Yeah, good. Mashad's always got some good folks there. Anybody who was a contractor in the past? Okay. Um, well, I'll kind of cover this generally speaking from the product standpoint, but as I'm kind of walking through some stuff, feel free to just interrupt and ask specific questions. It's kind of to give you guys the manufacturer's viewpoint of stuff. I'm going to talk about panel boards, the switchboards, and let you guys kind of get a feel about those products. Has anybody ever been hands-on with any products before? Okay, good. So this will give you a good shot at it. I'll try and show you what we're talking about and kind of help you visualize a drawing and a symbol on paper with what actually this is in the real world. So with that, I'll be talking about panel boards, switchboards, some of the options and features with the panel boards and switchboards, and then I'll offshoot into other things as we touch on those. So let's see. I wonder if there's the next page here.
You skip it, and when we want to skip it. Okay.
You can just say the arrow button left and go to the next one.
Yeah, that's what I was thinking.
So we see that. Okay, that's interesting. It's this way it's going now, but I don't know why it's not. Okay. It's a PDF file, isn't it?
It is a PDF, yeah.
Yeah. So I thought this one is slide.
Right arrow.
Okay. to go use these. Oh.
Yeah, that's the one.
That's weird. I don't know why it's not allowing me to. That has to do with my PDF file I know.
Okay.
View full screen. Okay. There you go.
There we go.
We got it.
Okay.
We just have to go.
Just got to break her loose a little bit. All right, so power distribution systems, just to give you kind of a quick overview, which you could be familiar with, and if you can see this very well or not. You know, everything starts with the generating station at the utility. They're going to create power in some means or method, generators, natural gas, hydroelectric power, nuclear, etc. They're going to take their power and they're going to step it up through a station switch yard, and generating voltage is usually from say 10 to 25 kV, and they'll step it up to transmission voltage, which goes as high as 765 kV. That's those big wires, obviously, that you see running across the farm fields from, you know, say western or eastern South Dakota all the way over to the Twin Cities. And once you get into the cities, you get into your neighborhood and you have a distribution substation. So we're going to step it down from what they call a transmission voltage to a utilization voltage. Utilization voltage is the voltage that whether it's a commercial facility, a residential, or a industrial facility can actually use. Industrial facilities often will take what we call medium voltage right into the facility. Medium voltage, from a manufacturing standpoint, runs from 1,000 volts to 35,000 volts. And there are motors that may be 5 kV and some are 15 kV that can be powered directly off this. Anything above 35,000 volts is typically considered a transmission type voltage. We also can drop it right down into a residential voltage, which is your single phase loads, your 120, your 240, something right inside your house, for example. What we're going to focus on today is your commercial facilities. And commercial facilities take either 480 or 208 volts. So 480, 277, 120, 208. And that's what we're going to focus on. Now, UL actually recognizes certain voltages. And these voltages have to be classified, has to be used on one of these by UL, and us as a manufacturer has to label our equipment with the actual voltage that is recognized by UL, which is then also met by the utility, and it keeps everybody on the same page and keeps the stray voltages, the different voltages out of the equation. You go to Europe, you might get something different. You go to Canada, you're going to get something different. So these are United States voltages. And your most common are your 480, 277, 208, 120 volt. These are all three-phase 4 wires. The same voltages can actually be a delta configuration, which is three-phase 3 wire, or you can get a single-phase voltage, 120, 240, or even a DC voltage to use in your facility. So a general distribution system that we're going to jump back and forth to today has some type of main switch on your medium voltage side, 5 kV for example, a transformer that will then step down into a 600 volt or less distribution switchboard, which then feeds distribution panels, motor control centers. Other dry type transformers are going to step the voltage down even further and basically provide all the power to your utility. So there's two main goals of a distribution system. The first goal is to distribute the power economically and safely. And it's the second goal is to protect the facility. And you can protect in one of two modes. You can protect for an overload or a short circuit condition. And the main goal in a short circuit is to clear the fault quickly and prevent damage and minimize the system interruption. So just a couple of examples of short circuits. You can have a line to neutral fault, and between a line and neutral is some impedance, and that's typically air that you think about. You can have a line-to-line fault. Line-to-line neutral is another example, and this one here, which I'm going to circle, which is the three-phase fault. So the three-phase fault, or a bolted fault, is the worst-case condition where all three phases are tied together. And when all three phases are tied together, there is the smallest percentage of impedance in that circuit. So think about somebody taking a copper bar, they're installing a switchboard maybe, and they're connecting accidentally, leaving your A, B, and your C phases bolted together. When they flip the switch up front, being all three phases are bolted together, it is what they call a catastrophic short circuit, and it's the worst possible condition. So with UL and all the standards committees, our job as a manufacturer and your jobs as designers is that you will always need to provide equipment to match the short circuit or the maximum short circuit available at that piece of equipment. And that maximum short circuit available is right here. That's your three-phase bolted fault. So the maximum fault current, it's going to be dependent on a couple of things. It's going to depend on how much current or fault current is available from the power company and the impedance in the system at the point of the fault. And NEC, I mentioned, also requires that the short circuit current available at the supply terminals, the protective devices meet that level. And as well as the protective devices, you also need to make sure the panel board and the switchboard or any device has the bracing to withstand those fault currents. So when we come back up here and look back at our system here, we're stepping down through a transformer into your 600 volt or 40 volt switchboard, where we have an available fault current of 65,000 amps. And through different pieces of equipment in the facility, we've got a panel board with 25,000, we've got a panel board with 50,000, and another panel board with 4,800 through a transformer. Okay, now remember what I talked or I mentioned that impedance is one of the factors that's going to determine a fault current. And when you think about impedance between this switchboard and this panel board or this panel board is going to be driven by what main factor? Cables. Okay, power's rolling through the cables throughout your facility. And when you think about a big cable, such as a utility distribution cable, or 500 MCM, 600 MCM, or KC mill, they're silver. It could be up to a silver dollar in diameter. If you think about that cable, it's a lot of copper. So all the electrons that are flowing in the inside flow pretty easily. A lot of copper in the middle and a little bit of insulation on the outside. And when you talk about a smaller cable, maybe I'm even talking about something this small for a 20 amp circuit. There's a little bit of copper in there, but you still have the insulation around the outside. So a little bit of copper, more of the electrons are scraping the edges, I guess is the way to think about it. So there's more impedance or resistance holding that fault current from going downstream. So in a case where I've got this panel at 50,000 and this panel at 25,000 amps, which one of these two panels, left or right, do you believe is closest to the switchboard? Remember, the closest panel to the switchboard is going to have a higher short circuit rating. Okay, if this is 50,000 amps and this is 65, that's going to be pretty close. This is 25,000 amps. That could be twice as far. It could be in the next room. The farther you get away, the lower your short circuit values are. Okay, this one over here is 4,800 amps. Now, why is that? Could be in the same room right next to this. In between, we've got under dry type transformers. So we've got a 480 volt switchboard stepping it down to 208, 120 with a dry type transformer. We talked about impedance. Dry type transformers have, just by the nature of how they're designed, are going to lower your short circuit on the secondary. For transformers, when you peel the skin off and look on the inside, there is voltage going through one coil that is going to induce voltage on the other coil on the other side. So there's no true hardware connection between the two. So because you've got that air and that magnetized voltage you're creating on the second side, no matter what kind of fault you make, there's going to be enough resistance that is going to set a fixed value of fault current coming out of that dry type transformer. So one of the design tools that we always use to talk about is if you've got a fault current condition, maybe you've got an existing building like this and it was all designed for 35,000 amps, the utility comes in, they change out their transformer, outside, and they put a bigger transformer in. So now they come and say, okay, Dunwoody, you guys have 65,000 amps available because I just changed the transformer. And you're sitting here going, well, I've got all this 35,000 amp rated equipment. Code's going to make me change it. So what are a couple options from the design side we use? If you're closer, maybe not 65 to 35, one of the options you could do is take cables and make a lap around the ceiling, for example. You're adding more cables. Each foot of cable is going to add a little more impedance. Each little more of impedance is going to lower that fault current a little bit lower. Kind of one of those tricks you use when it's close. Another thing we do is we can add transformers into the circuit. So if you've got 480 volts coming in and you're just way too high, you can put a transformer there with a smaller kVA rating that is going to inherently lower the fault current on the secondary of that transformer. All right, any general questions on power distribution? Okay, we'll just jump a little bit into panel boards. A couple things in the panel boards. I'm just going to talk about the definition, a little bit of the components, and some application stuff. You guys familiar with the panel board? When I talk panel boards, you familiar with the concept? Generally speaking, okay. Panel board is a wall-mounted electrical distribution device, basically used for circuit control and overcurrent protection for most commonly light, heat, or small power circuits. And the big difference between panel boards and switchboards are your panel boards are your wall-mounted devices. Largest you can get is 1,200 amps. Switchboards are your floor-mounted devices, can go up to 6,000. In a panel board, it's going to come in three pieces. There's going to be a box, a chassis, and a trim. And from a manufacturing standpoint, we ship those at least in 2 shipments, often 3 shipments. First thing to go is the box. 4 weeks later, 3 weeks later, 2 weeks later, you'll get the interior. Why is that important? Why does that help? Because the contractor, when he gets that box, he can spend a day or so mounting the box, connecting some conduits, doing some install in the box itself before he gets to the interior. Okay, and this is the interior of a panel board right here. It's a small one, so I can get her up to this room here. But generally speaking, this is, when I talk about a chassis, this is what we're talking about on the chassis. So you can see from the front, here the definitions, live front and dead front. Dead front is when I've got sheet steel covering all my stuff, so if this is mounted on the panel board, I'm not going to be able to grab my hands on 480 volts. When you talk live front, you could say this panel here wasn't here, and I can reach in and grab right under the 480 volts if this was active. So generally speaking, anything in our commercial distribution world is going to be dead front for safety. So I'll come back to this here. So once the box gets installed, chassis hits, and the chassis gets installed, I guess just to show you how this works. The chassis itself is mounted on a couple of rails. The rails really is what mounts inside the panel board. So on the chassis, you've got a main breaker, which is connected to A, B, and C, 3 bus bars, and in the back of the bus bars, you see these bolts. Well, those bolts are actually the circuit breakers bolting directly onto A, B, and C trays. And you can see there's insulation here. This happens to be a plastic insulation. There's also folks who use some type of a paper insulation. A bunch of different ways you can do that. So in addition to, say, an 1.5 inch of air, you've also got some extra protection here. The more insulation in here, the smaller the equipment goes. You can see as you start designing things, you're going to get a trade-off. Everybody's going to want it smaller. The architect's going to say, I'm giving you a smaller room. That's almost every project. And the field installing contractor is going to pull you the opposite direction. They're going to say, make things a little bigger so I can get my hands in here and do some work. And as a designer, you're going to have that trade-off of optimizing space for the architect and a good product for the contractor. So these chassis, once they mount in the can, then you get to the point where you're going to install a trim on. And the trim is that's what folks see. Panel here. So in this panel here, the trim is the only thing that a normal folk would see when they're looking at that. So there's 3 types of chassis. There is a main lug only chassis, a main breaker chassis, and a main fusible switch chassis. Which one is this? Okay, main lug only has lugs. Main circuit breaker has a disconnect. So the main difference between main breaker, main fusible switch on one hand, and main lug only on the other hand is you're going to have a means to turn this circuit on and off. If you turn the circuit on and off, then you can safely work downstream at certain loads. Okay, a panel board can be set up one of 2 ways, either from the top or from the bottom. Us as a manufacturer need to know that ahead of time because we're going to configure this panel board accordingly with the incoming line on one side or the other. We'll build that up to meet the need. The other thing that us as a manufacturer is going to need to know is the trim surface or flush? Okay, when we talk surface, think about taking your panel board can and just bolting it on the outside of the wall. Doing all your conduits and everything outside of the wall, and then the interior of the trim mounts right on the wall. And the can itself is about almost 6 inches deep, so it's going to all protrude off the wall. When we talk a flush trim, it's just like this. You take the panel board can and it recedes in the wall, whether it's between the somewhere behind the sheetrock. And the only thing that protrudes from the wall is this trim, which barely comes out of the wall. And you'll see one thing that's different is this dotted line around the outside. Flush trim is going to have about 1 inch, 1.5 inches around the edges for basically to cover up that overlap where the box or the hole in the wall is. So it's a little bit of an architectural play as well. A couple of special trims that are very common in the industry is concealed trim clamps. Okay, looking at this standard trim, you've got a couple of screws that you can take off to pull that trim off the panel board. Why would people need to pull the trim off the panel board? Number one, when you're doing an installation, a contractor is going to wire all his individual circuits, and he's got a He's got a morning break, a noon break, and an afternoon break, and he may, take a week putting together different connections. Every time he goes in and out of that panel board, he's got to have a trim on it. Once it's set and installed, it may be a year, 5 years, 10 years down the road, the owner may come in and do some recircuitry. May get another line of computers, may get some different receptacles on the wall where they're going to do some circuitry. So those trims do come off periodically. So those bolts on the side are there to remove the trim. Now, if you're maybe a case here, we're in a classroom, or in a case where you're putting a panel board in a hallway or a prison where you kind of want to limit folks' access to that, because if, I remember in high school as a good example where somebody had a dime, hey, let's see what happens if we take these screws out. And that's a dangerous situation. So one of the common things you'll see in that kind of application is something called fast concealed trim clamps, and you don't see any screws that are on the outside here. So it makes it much more difficult to gain access to the insides of that panel board. One of the other options that you see on panel board trims is door-and-door trim. And see, we got some screws here, and we got some screws here, but right here is a hinge. So when they say door-and-door, we've got two things. You've got this small door, which exposes just the dead front. So just this part here is exposed. It's all safe. You can turn breakers on and off. But the other thing you can get is a larger door, which opens everything around the panel board, exposing the wireway, the load connections of the panel boards, and everything in there. So from a contractor's installation standpoint, this door-and-door is a big time saver to be able to get in and out of that panel board without having to take the whole trim off.
It's safer too.
Much safer, yep.
If you're working energized, swing it in your work versus trying to align it and accidentally put the panel, the corner got into one of these phases, you shorted it. So
yeah, if you're doing it hot, especially. If you're working on an energized, you need to minimize any chance of danger. One of the things Eaton, this is an Eaton exclusive that I'm gonna show you, make sure you're aware of, is called the Easy Trim. We came out with this must be 5-6 years ago now, where we take this is our standard trim. So if you order a normal panel board and don't say anything, you're going to get this trim. It's a concealed hardware door-and-door at standard trim, and there's no mounting hardware that's even required to mount it. So the screws don't exist. And literally, it's about a 20-second job. And if you ever go to the Midwest Expo, we had a demo up there for a year or two. And contractors, we kind of had a contest and contractors got down to like 6 seconds to be able to install the trim. And, if you're thinking about, if you're in the middle of a panel board and you're a contractor and you have to run from here to across the hall and back and forth as you're hooking this up. And every time you shut that panel board, it takes you, whether it's 2 minutes versus 10 seconds or what have you, it can save you a lot of time. And we do that by putting these little hangers on the edges where that piano hinge was on the door-and-door. So the trim itself kind of just sets on there, and then when you close it, it kind of snaps and drops down and locks in place. So we're getting a lot of folks like that trim and the ease of use. So when we talk about panel boards, often we talk about multi-section panel boards. So when I talk multi-section, in the old days of 3 years ago, NEC limited lighting and appliance panel boards or receptacle panel boards to a maximum of 42 circuits per panel board. And a lot of times you get an electrical equipment room or something where you need more than 42 lights or receptacles coming out of one panel board. So it's common to have 42, 84, or 126, I guess. You know, 1, 2, and 3 panel board tubs all connected together. Today, or as of about 3 years ago, 2011, NEC opened it up and removed that restriction. So now the only thing restricting how many breakers we can put in a panel board is physical space. And generally speaking, for panel boards like that, we can put now up to about 84 circuits inside one panel board tub. Not sure I'd always recommend that because it becomes a lot of cables running through the wireway in a single panel board. But again, it's another tool to put in your basket for space savings or to help you out in the design criteria. So, if you do get to a case, maybe you've made your own design standards where you don't use over 42 as a general rule. So you have multiple panel boards that you need to connect together. We've got a couple of different options to do that: sub-feed lugs or through-feed lugs.
But how do you see the engineers are doing it now? Are they taking advantage of the 84? Are they specifying 84? Or are they...
Generally speaking, most folks are staying with 42. Yeah, I'd say about there might be 10-15% of the folks who will go over 42. A lot of times the existing facilities or the industrial facilities, they don't worry so much. They don't, space is more important, so they'll take full advantage of using 84. And a lot of times it might be 54 or 60 circuits seems to be a good break number where they'll put that all together into one panel board tub. But on new construction, I'm still seeing a lot of 42 circuits. In this one, we don't see as much, but we've got sub-feed lugs and through-feed lugs. Sub-feed lugs is one set of cables, 2 sets of lugs on the first panel. One gets in to feed the bus on that panel, and the other one daisy chains over the second panel. So each panel then is fed via this incoming line. And physically, here's what you look like. So this is A, B, and C phase. Each phase physically has 2 lugs bolted to the copper bar there. More commonly, with multiple panels, we see what we call through-feed lugs. This is probably 90% of what we do. For through-feed lugs, you can have a main lug only or a main breaker. Okay, main lug only doesn't give you any disconnect means, and main breaker again gives you a means of disconnecting all these panel boards. So in this case, your one set of cables will feed the bus all the way to the other side, where you hook in a second set of cables that jump over to main lugs or main breaker on this side, which feed down to the panel board bus. One of the general guidelines that folks follow when they're doing these is you may have a main breaker in one panel with main lugs in this panel, and from panel board manufacturer standpoint, we've got different heights, like 6-inch increments in panel box heights. From a design standpoint, if these 2 panel boards come out 6 inches apart from our engineering side, you may choose, we may, default to this, make the second box bigger so both panel board boxes are the same height. And that really gives a much better appearance for the owner, but it also allows these cables to shoot directly across from lugs on one side to lugs on the other side, for example. And here's what your through feed lugs look like. Lugs here, lugs here. One of the most common applications I've seen in this is for high rises. And you don't have to be a 50-story, but maybe you've got a 5-story um, building, whether it's like an office tower from floor to floor, and you can run a panel board. Think about life safety. You've got to have a separate feed. You don't have a whole lot of load, and you'll have 4 floors of panel boards. They'll run power to from the floor 1 on the lugs out the other side, and this goes up to floor 2, and the bottom out the top up to floor 3, and it saves you some cable, and it saves you a lot of extra feeds up to those different panel boards. Okay, on the panel boards, the sizes I mentioned are restricted only to practical limitations such as standard box heights or widths. One of the things that we have to follow as a manufacturer, but more importantly has to be followed by the contractor in the field, is that any C has a limitation on the top breaker in a panel board. The operating handle can be no more than 6'7" above the finished floor. And inspectors will red tag that. If they see something close, they'll measure it and red tag it. When you talk 84 circuit panel boards, for example, those are pretty tall. Those are 90 inches tall. And if when we design as a manufacturer, we might assume on a big panel board like that, you have to put the bottom on the ground or ground level. And if you raise it up by a foot, all of a sudden the top panel board or the top breaker is out of tolerance and you're going to get red flag. So it's probably maybe another reason why you don't see those larger panel boards a lot. And from a contractor standpoint, something you always need to be aware of. Panel board standards, most common as manufacturer that we have to follow is UL. From a field installation standpoint, the National Electric Code dictates all. So that's the installation versus the manufacturer code. We also have NEMA that we stick with, as well as some federal regulations that sometimes apply. So now as we look to Eaton products, just so you're familiar, because when you get out there, you're going to see all manufacturers have different verbiage, and you're going to have to learn them all, or just say, okay, well, I'm just going to learn Eaton's and stick with Eaton's. That's fine with us as well. So our verbiage is called the power line family. So we really divide these into 2 categories, and one would be called the lighting and receptacle panels. It's a name that's been lingering on for years, even though it's not recognized by NEC anymore. And the other is the power panel boards. So the lower end of our panel boards, power line 1, 2, 3, are called lighting and receptacle panels. Generally speaking, low amperage, 400 amps or less, a lot of 20 amp 1-pole breakers. The upper end are called power line 4 panel boards. 4B, 4D, 4F. Bonus credit if anybody can tell me what the B, D, and F mean. B for breaker, F for fusible, and D I would have given double bonus. That actually means drop. So these panels are, you can see they're much bigger. Power panel boards, I generally consider them power distribution panel boards. So these may be at your point of load, maybe one in a room like this. This may be on 1 per floor. So you're feeding from your main switchboard up to a power distribution panels, which has 5 breakers in it that feed 5 lighting and receptacle panels. And that's a typical application for that. For a manufacturer to price a panel board, we're going to need these things to be able to give you the equipment that you're looking for. So this is a good cheat sheet when you get these slides to kind of look at from a manufacturing standpoint. Here's the information that I'm going to ask for if you call me up or drop me an email. The service voltage and frequency. What's the frequency in North America? 60 hertz. believe it's 50 in Europe, and I don't know if there's anybody who does anything other than 50 or 60. But service is three-phase 4-wire or three-phase 3-wire. Voltage 480, 208. Main amps rating, okay, and that could be the standards for Eaton are there's 100 amp mains, and I'll call this panel board busing as well. There's 100 amp, 225 amp, 400 amp, 600 amp, 800 amp, 1200 amp, and then everything above that is a switchboard. The type of main lugs, main breaker, main fusible switch. Basically, main fusible switches were the way folks used to do it, 30, 40, 50 years ago. Every year, less and less people use fuses. There's some good applications for fuses, but fuses inherently have some drawbacks as opposed to breaker. Well, fuse and breaker, you can isolate the circuit and both offer protection. But a fuse, the number one thing I see in a fuse is you can't put any options in it. And when we talk a circuit breaker, you can put different options like a shunt trip. You can electrically operate it. You can put a little metering package in there. You can put ground fault protection into a trip unit on a circuit breaker. Anything, all kinds of options you can do with the circuit breaker. And the other thing is, if you've got a fuse and you have a fault condition, maybe you accidentally stuck a screwdriver in a light socket, tripped the main breaker. Okay, if it's a main breaker, that's fine. My mistake, I walk back up, I reset the breaker, everything comes back on. If I get a fuse, I walk back up, I have to change the fuse before putting things back on. The first thing I think about is safety. When you're changing that fuse, you've got 480 all around you. Second thing I'm going to say is availability. What happens if you don't have that fuse? It ain't there. You're down until you go to your local distributor or wherever you can get a fuse and get one and come back and put it in. So with those two primary factors, circuit breakers are really becoming predominant in the industry, except for special applications. The other thing is the short circuit current rating. Okay, I mentioned everything needs to be sized to meet the available fault current at every specific piece of location. Your branch circuitry. A lot of times you're doing 20 amp 1-pole, sometimes you may need 3-pole breakers. All your loads need to be fine so the feeder breakers can be part of the panel. The environment. You guys heard the NEMA classifications for enclosure environments? The standard that we say is NEMA 1. That means it's not really protected from any environment. You're just enclosed for safety. NEMA 12 is another option that adds dust proof. So maybe that's a strip of gasketing around the trim. NEMA 3R is the standard that makes it outdoor rainproof. Not waterproof, just rainproof. So that's kind of an important distinction. You can't take a hose and squirt it at the panel board, for example. Those are the three most common. We also have some other specialty enclosures. NEMA 4 or NEMA 4X are both corrosion resistant. NEMA 4 is a plastic. NEMA 4X is actually a stainless steel. So if you get into an environment like a water treatment plant where you've got a lot of chemicals in the air and you're going to put a panel board outdoor and the chemicals and regular steel don't mesh well, you can have a panel board that turns green within a year if you're not careful with the environment. And so a lot of times you'll put stainless steel in those locations. The last thing is fully rated or series rated, which I'll jump into here shortly.
Todd, did you see non-metallic panels?
Uh,
Will you be able to have a non-metallic panel?
Yes, only on the outside. Let me correct that.
Yes, sir.
Only on the panel board can and the trim.
The can.
Yes, the can itself, the box.
chassis will continue to be metallic.
Correct.
Does he have
Yep.
to have means for grounding still? So just the outside
Or-
or for grounding the box?
Yeah, say it again.
You have to have a means for grounding that box for safety still in? Is that what they do with it? Or just the case?
Yeah, I mean,
Well, yeah, just for like safety purposes for the board.
yeah, a box around it.
Yeah.
Yeah, you're always going to need a box around it.
No, I was saying, that's what.
All right, roll rephrase.
Oh, no, I just meant, like, for grounding purposes, they have to have it still metal, just so that they can ground it.
Ah, yeah. Well, and actually, I got a picture coming up for that because there's two things. You've got the equipment ground. A lot of times, you're going to ground the can, which is what you're talking about. You can actually take your building ground, I'll call it, and attach and bolt it right to the can. You can get by with a ground bar instead of using the can. So we provide that means still in there. Because you're absolutely right, you always need some point of ground reference. Ground reference is, base style, consider ground reference is voltage 0. This is the way you have to look at that. And all your voltages, 120 or 480, are all referenced off this ground voltage. So in some cases, you may get a fault condition if you don't have a neutral, where the ground voltage is going to change, and that could throw off everything in a ungrounded system, I guess, where it could throw all your voltages off and your whole system can get out of whack. So generally speaking, you always need some kind of ground reference. So from the short circuit rating, short circuit, there's two things we look at from the panel board is the withstand rating of the chassis itself, and that's maybe how many insulators and standoffs we put in there to hold the bus bars together, and the interrupting rating of the overcurrent devices, which is the main and the branch. And generally, all of the lowest rated device will determine the overall rating, but I'm going to put an asterisk on that. And the asterisk is that you can get by with something called series ratings. So it's probably a good point for this. We've got a couple of different breakers here I was going to show. In the running and receptacle panels, we've got, for 208 volts, we've got a standard interrupting rating. The minimum is 10,000 amps, or 10 kAIC. So these breakers here, 1 pole, 2 pole, 3 pole, are circuit breakers that are designed to withstand 10,000 amps fault current. And it's a slide coming up, but basically when we talk about withstand, you can flow 10,000 amps through these breakers. They're going to let it flow through, and they're not going to blow into pieces. They're going to be able to do the next job, which is actually interrupt the fault current. So circuit breaker number 1 has to be able to stay together. 10,000 amps is a lot of amps to do something like this. And after it stays together, it needs to trip. And trip is obviously the safety mechanism. And those two are tested rigorously by UL. And continuously through our process, or manufacturing every day, I'm sure we do some testing. Now, if I say I don't have 10,000 amps, and I have 65,000 amps available on my panel, well, this is a 3-pole 20. This is a 3-pole 20. This one you can get a 35 kAIC, 65K, or even 100 kAIC fault current. So these could be, this one goes up to 100 amp max, this one goes up to 225 amp max, but they could be the same breaker for the same application, all dependent on the available fault current. Same thing goes for your 1-pole breakers. Same 3-pole, 1-pole, they're kind of just break off a third of the circuit breaker, and this is a standard 20 amp 1-pole breaker versus this 20 amp one pole breaker, which is lined up in that panel or any of your hallway panels. So that hopefully just gives you a visual of why it's important to know the fault circuit, the short circuit rating. So fully rated protection is when all the devices meet the available fault current at that panel board. Series rating is a value engineering option that UL allows. And that is when the short circuit interrupting is assigned to a combination of two or more devices when connected in series. Okay, the upstream device, such as the main breaker, needs to have the full rating. So if you have 65,000 amp fault current, you need to have a 65,000 amp main breaker. However, what UL allows is testing between this main breaker and the feeder breakers. I want to use these feeder breakers versus lining up a bunch of these feeder breakers. And if we test those, we can call it series rating. Visually, this is a panel board that is fully rated. Everything is 65,000 amps. This is a panel board that is series rated. So I've still got my 65,000 amp main breaker, but I'm using these 10,000 amp branch circuit breakers. Okay. What's the main thing when you think about, I guess, if you're an accountant and you look at these two things, this one's obviously going to be much more expensive than this thing. And when you're designing, whether it's design build contractor or as an engineer, you've got a couple of different goals, but one of your most important is you need to design a cost-effective system. Every owner, every guy with a checkbook is going to have a budget. And usually once you go through the first design, you're going to be above the budget. You're going to be a little bit high. Let's see if we can squeeze some more money out of it. This is one of the tools in the basket to be able to take some more money out of it. Okay, I mentioned these are tested. So from a manufacturer standpoint, we have to have all this documentation that says if you use only this circuit breaker with this circuit breaker, you know, this is a BA and this is an HFD, you know, so we specify the exact circuit breakers, then you can do it. And we publish all this data, and all manufacturers have to publish this data and keep it with the panel board, because mistakes can be made, and if you make a mistake 5 years down the road after the panel board is installed, you may end up with a panel board that's not properly rated. The panel board itself, or the main device itself, the upstream device, doesn't necessarily need to be in the panel board. You can put it upstream. Okay, so here's a this would be a typical panel board with your branch circuits and your main that's series rated. However, you can do the same one with main lugs and go upstream and rate. Okay, just from a panel board standpoint, this panel board with a main breaker and this panel board with a main lug. Same panel board, one with lugs, one with a breaker. Which one do you figure is going to be more expensive? Main lugs or main breaker? Flip a coin. Main breaker. Main breaker. It's more stuff, it's going to be more expensive. So from a cost-effective design, or another way to save money, each time you can make a panel board main lug only, you save a little bit of money. So in this case, both of these panel boards may have this same breaker upstream. It's in the main distribution switchboard at your service entrance, and you're feeding all the way down to either a panel board with a basically an identical breaker, or you can put main lugs only there. Now, there's reasons people put main breakers in panel boards other than protection, is it does give you a local disconnect. So you can always walk up to a panel board with a main breaker, open the main breaker, throw a lock on it, and work on your panel, on your downstream stuff. And that's a big benefit that you don't get with main lugs. If you have main lugs, you have to go all the way upstream to the switchboard or whatever's feeding the panel board to do any lock off or isolation.
But then also thought the advantage of having it upstream is you can completely physically isolate that piece of equipment from electricity. So you can take the whole panel.
Yep,
Versus you can't do that one if you have the main inside the panel.
absolutely.
That's a major advantage of having the circuit breaker outside the panel too.
Yep. And Chad made a good point. Even if I open this breaker, if I want to come in and work on this breaker, and I open that breaker, you look on the back side of this, you've got 40 volts right here at the top. Okay, the breaker's in the middle, so you're opening the circuit in the middle. But here, you still have 40 volts. And there's no way around that, I guess. So,
And I believe when you put your arc flash label, it will take it on the line side, not the load side too. So
Yeah.
you have to put your PPE on it even if it's damaged because you could reach on the line side. So it's that's what we say when you put it outside. This is dead.
Yep.
Lock it, tag it, and work on it.
absolutely. Every piece of equipment now has to have an arc flash label. It shows you the energy, what type of personal protective equipment you need to wear. And the only thing we look at when we're providing analysis and putting stickers on is the line side of that circuit breaker. Just to give you an idea, when I talked about cost for that, the two options that we just looked at, okay, fully rated option, you got a bunch of these breakers versus series rated where you can use a bunch of these as feeders. Kind of drew that up and figured let's put a visual to that. Your main breakers, we worked out some pricing here. Your main breakers are the same, okay, and your feeder breakers at fully rated basically brings your price up to $10,000. Same panel with a different feeder breaker, series rated, brings your price to $5,000. So this one may be an extreme, but you can see series rating cuts your electrical equipment cost in half on this panel.
That's why we use series rated equipment.
Yep.
That's the main reason. Otherwise, fully rated equipment is superior in terms of performance, but it's more expensive.
Now the trade-off is you're not going to get any selective coordination out of those two circuit breakers. Okay, there's fully rated and series rated. When you got fully rated, you sometimes have the ability to adjust the trip curves and ultimately let the downstream breaker trip ahead of the upstream breaker. So if you haven't heard the term, or if you have heard the term selective coordination, has to be done with a fully rated system. So what selective coordination is, generally speaking, is to optimize a design in a facility, you want the circuit breaker closest to the load to be the one that trips and takes the load offline. For hospitals or critical operations facilities, this is mandated by code for not all of the distribution of a hospital, but anything that is considered life safety, critical, essential equipment. And when selective coordination comes into play, you cannot use series rating whatsoever. In series rating, I've got two breakers, they're tested, that something will trip, but I can't tell you which one will trip. I'm just telling you something will trip and take it offline. In selective coordination, I'm telling you this one will always trip first ahead of the upstream device. If you think about a hospital, why that's important, or when the generator kicks on and you're running emergency power, and you've got 3 operating rooms going on right with surgery or some type of procedure, and somebody trips a breaker, maybe accidentally put in too much equipment and overloaded the circuit. The You really need that device that's on that specific circuit to trip. The other operations that are tied into that same panel board can continue as in their process. If you go up and you trip the main breaker instead of that specific load breaker, then this little incident all of a sudden shuts down all your other operations, your critical procedures. Every panel board that's series rated, we do put in this series rating manual, and the series rating manual is always going to tell you the combination of breaker, feeder breaker, and main breaker to give you your series rating. Okay. As we talk kind of about the circuit breaker, maybe this is kind of a good time to just show you circuit breakers can trip with one of two means. If you've heard of really you're talking about the trip unit or the tripping function of the circuit breaker. One is called the thermomagnetic trip unit, and the other is a solid state trip unit. The thermomagnetic trip unit, and these are inside of both of these, is just like it says. You've got a thermal and you've got a magnetic protective feature. Jump back to one of my earlier slides. I said there's two kinds of faults that you can have. You can have an overload or a short circuit condition. An overload is an extended period of time where you're barely over the rating of the circuit breaker. So maybe I've got a 20 amp circuit breaker and I'm plugging in a 25 amp piece of equipment. I'm plugging into the socket. I can run that for 5 minutes, 10 minutes, maybe even 15, a half hour. You're not really sure exactly. You're going to gradually overload the circuit to where it's going to trip. In a short circuit condition, okay, I've got my same 20 amp breaker, and now I'm taking two wires at my receptacle and I'm banging them together, creating a ground condition to where all of a sudden instead of 20 amps flowing through that breaker, I've short circuited to where I've got 200 amps or 2,000 amps going through that circuit breaker. In that case, that breaker is going to trip off as quick as possible. It's not looking at time. It's going to see I've got way too much current. I'm going to trip off quick. So inside the circuit breakers, we've got two functions. We've got a thermal function, which is basically two pieces of metal inside the circuit breaker, and bimetallic might be a way that you'd hear it. And what happens is different kinds of metal, so as the circuit heats up, at 20 amps you're fine, at 25 amps this metal is going to gradually bend, and if you're over the rating of that metal, it's going to gradually bend. It's going to bend to the point where it's going to hit the trip bar and trip the circuit breaker. That's the thermal part of the thermomagnetic. The magnetic part is what looks at short circuits, and the magnetic part of the circuit breaker is looking at current that, say, is in the 200 amp on a 20 amp breaker, so 10 times. That current is going to create a magnetic field. The magnetic field is going to do the same thing. The more current, the more magnetic field is, and it's going to push that trip bar as well. The magnetic field is going to do something on the inside of the circuit breaker to hit that trip bar. So I'd say it's important to understand the concept of thermomagnetic, both protective features under one circuit breaker. And these are all mechanical type features. There's no circuitry. It's literally a couple pieces of metal for the thermal and a coil that creates a magnetic field for the magnetics. And it's that simple. I mean, it fits in something like this. Now, for the larger circuit breakers, rather than, you still have the option of having a thermomagnetic trip unit in there, but in addition to the thermomagnetic trip unit, you can also get what they call a solid state trip unit. Okay, this one's a solid state trip unit. I don't think it matches this circuit breaker, but basically you can just rip out this one here and put this in here. The solid state is a little different in that you can see cables actually connect through the breaker and can come out here, for example, and inside of this trip unit is CTs, current transformers. So in a solid state trip unit, you are sensing the current that is flowing through the trip unit and digitally modeling it inside this trip unit. So the trip unit itself is looking at the current and creating its own waveforms inside the trip unit. With the creation from normal current, and you're creating a digital model inside the trip unit, you have much greater selectivity on your tripping curves. So these solid state ones all come with dials on the front that you can dial up and down, and you can change the pickup settings for the amperage, and you can change time delay settings. And what that allows you to do is take your standard trip curve and move it around. So we know when this one's going to trip. There's a line here, and it's going to trip when you cross that line. This one, for solid state, the default settings might be here, but you could take that setting and say, I need to coordinate better with my upstream and my downstream equipment. So the downstream equipment trips first in the case of a fault. And I want to move this curve a little here, bend it here, and turn it up. You know, however you need to do it to make that work.
And if I may inject something, everything that Todd is talking about, guys, you will be doing in a software called STM Portals when you're doing this class. So this is called coordination. You look at all these steps. Should we give them a 5 minute break?
Yeah.
Todd,
Yep, that's good.
Do a 5 minutes break. I'm sorry.
Yep, no, that's good.
Thank you. That's, I always enjoy hearing all this good stuff. Let me get. And what did we do this last time? We came here and we said, I forgot what we did. Okay, full screen.
I think that was under view.
Under view, okay, view. Where is full screen? Here you go. That's what we did.
Okay.
Okay.
Yep.
Perfect.
All right. So the snapshot of the panel board family, you know, generally speaking, without going into the details, we start at 1, 2, 3, 4. We have this 5 version that I won't get into. It's kind of special. But you can see your 1s and 2s are maximum 240 for the 1s, 480, 277 for the 2s, 400 amps, 100 amp maximum branches. And then as you get bigger, you increase your amperage ratings and increase the size of your feeder breaker ratings as well. And you'll notice we've got default cable sizes depending on the panel board and the amperage, but it's just important to note the cable size when you're designing. Sometimes you're going to oversize your cables for voltage drop reasons or any other reason that you may have in your pocket. And if you're going to oversize your cables or use a different configuration, always check those. With main lugs, we can often accommodate it. With main breakers, you're kind of limited to the space that's in the top of the circuit breaker. So you may use a cable that just doesn't physically fit in the circuit breaker, and we may have to use this circuit breaker instead of this one just to fit the cables. Okay, so now the ones, this is the snapshot of that panel board. As I mentioned, 100 amp max branch breakers, 400 amp max main lugs or a main breaker, and 240 volts. So that's single phase or 208 123 phase.
May I say something about this one?
Yep.
Because this is related to the project that we're going to use. So this panel will be used for the 28120 system that we have for the lighting panel and the receptacle. We have a 100 amp receptacle panel and a 225 amp lighting panel. They will go 208 123 phase. So that would be right. Am I right here with choice?
Yep.
The first choice for,
Yep.
for these two panels. So when you guys have cut sheets, that's what you're looking at for your cut sheets.
Okay. And look right up here. You've got all your branch circuits. Okay, that's just like this panel here. Okay. What's missing up there? Circuit breakers. What kind of panel is that one? That's main lugs only. That's the difference. I can open and close this breaker. I got no disconnect means on that. And we talked about the ground bar. Here's actually how we do this. Okay, you've got the can, you've got the interior that mounts right on there. We'll provide a ground bar for one gutter and a neutral bar for the other gutter. Okay, ground bars, normally they'll bolt right onto the can and metal to metal. So your equipment ground bar will be right part of your can as well. Okay, you familiar with the term SPD, Surge Protective Device, TVSS? Give me that information. Okay, give you a little spiel on the SPD, Surge Protective Devices. They used to be called TVSSs up until 3-4 years ago. And you all changed classification to SPD or Surge Protective Device. Your computer is plugged into, well, I'm not sure if that is or not, but maybe your computer, your TV at home, is plugged into a little surge strip. You read the manual for your brand new plasma TV that's plugged into that surge strip, and it'll tell you warranty of this $2,000 TV is only valid if plugged into the appropriately sized surge protective device. Okay, there's a reason they do that. You know, it's what surge protective devices do is chop down transient voltages with all the electronic equipment, Xerox machines, fax machines, copiers, computers themselves, everything solid state, which is switching, everything switching on the inside computer, creates very small time duration transient voltages. So large spikes that are very quick. They're tough to see. They don't really do any damage to normal stuff. They were invisible on a motor or a receptacle that you're plugging a hairdryer in. You ain't going to see much of a difference. In solid state equipment, transient voltages can actually damage a TV or a computer and cause it to fail. Okay, and there's two kinds of transient voltages. Most obvious one, when you talk about plugging your TV in, is, I'll call it externally generated transient voltages, the most common, which is lightning. So if lightning hits on the power cables across the street from your house, once it gets on the power cables, it's going to shoot wherever those power cables go, all the way down into your house, through your panel board, into your TV. And what that's going to send is a big voltage spike through the system. The other kind, and that voltage spike without protection will go all the way into the circuitry of your TV. The other kind is the internally generated transient voltages, like a Xerox machine. The way they work, or fax machines, the way they work just sends a lot of transient voltages. Now they're going to go from that machine, they're going to funnel back to this panel board, They're going to go up the copper cables all the way to the main switchboard, and then funnel out to all the other equipment in this building until you find something that's protected by a surge protective device. Like I said, a lot of times negligible, but oftentimes, and I think about a college environment with everybody's computers and laboratories with sensitive electronic equipment, all this stuff can be susceptible to failure. The internally generated, I should say the externally generated, the lightning is like in a boxing analogy, it's the knockout punch. You're going to get one big hit, and you're either going to make it or you're going to fall down and get knocked out. The internally generated transients are the jabs. You're going to hit it 100 times, 200 times, you're just going to take it, and you're going to be fine, and all of a sudden, that last 200th jab, you're going to get knocked out. Both of them can be damaging to your solid state equipment. So what UL's come up with, and this has been around probably 30 years by now, is transient voltage surge suppressors. Here's an example. We now call them SPDs, and I'm going to slip on that, I know. So the SPD surge protective devices have these things in there called MOVs, but what they do is they take the transient voltage spike and chop it off greatly. So you may have a 10,000 volt spike that gets knocked down to 800 volts. 800 volts on a 480 volt piece of equipment sounds like a lot, but it helps it greatly. And one of the things you do from a design standpoint is you look at your facility, you determine the level of solid state electrical equipment, and then you put in the appropriate surge protection. In the case of a classroom or anything with this type of equipment, it's very common now to put the surge protective device right in the panel board. And you can see this one's right in here. It goes right in the panel board, and really all we do is shift this breaker up a little bit and slap that right in there in the chest. And the surge protective device has these little MOVs that shunt that big unwanted high voltage spike to ground. So it opens these little gates real quick and sends all that energy to ground and lets only a little bit through. We mount it directly in the panel board and directly on the bus, and that's the best design because for transient protection, if you have cables tied to the bus, every inch of cable increases the let-through voltage by 20 volts. Okay, without getting too deep here, I guess mounting it right on the bus basically lets you use your published let-through voltage. So maybe it's 800 volts, your let-through voltage. You extend this and mount it outside the panel board of 20 feet. You add a little more impedance into the circuit, and your 800 volts, 20 inches, 2 feet, might knock it up to 1200 volts let-through. So you're decreasing the protection on your equipment by mounting it external to the panel. Sometimes you have no option, but a designer, you always want to optimize the protection for your customer. Now, what does this do on this panel board? Well, why it's there on the panel board, if you have any lighting, if this is a main switchboard or something, and you have any lighting coming in, it's going to shunt as much as it can to ground at the panel board, so your loads coming out of your branch breakers aren't going to see that. Similarly, the internally generated transients that are coming from your copier machine or any other equipment, once they go through that branch breaker and hit the panel board bus, this again will shunt the high voltages to ground. So the other branch breaker, also feeding off that common bus, doesn't see it. So it's a 2-for-1 package, and it will add life to whatever electronic equipment you're having connected to your panel board. And put it in the panel board. Also, you've got no installation cost from a transformer from a contractor standpoint, so it's purely a material play. And we always believe in the cascaded approach, so if you're designing a building from scratch, always put one of these on your service entrance piece of equipment so you can have that first stand of protection against lightning strike. The next step is to always do a second layer, a cascaded approach, and that second layer, depending on the type of facility, could be in this panel board or the critical panel board of your loads. You could have a third layer in between if you've got a big campus building where maybe you've got power distribution panels in there. Or always have this final layer where your computer is plugging into some type of surge strip, for lack of a better word. Surge strips, they're not great protection. They're just a fraction of the ratings of something you can put in the panel board, but it's a great last step of protection. All right. Anything else in surge protective devices? Give you something to think about or whatever when you run into that.
Our project requires us to have one. The project name is that if you read through it, see, we need one on the bin.
So similar to the power line 1, which is 208 volt lighting panel, the power line 2 is 480 277 volts. Same 400 amp maximum, same 100 amp branch breaker maximum, just a higher voltage. So you've got the ability to do 480 277 volts. Great for receptacles or some 277 volt lighting. Power line 3 panel boards. Now, here's a panel board. I'm going to call it a hybrid. You don't know if you need a power distribution or a regular panel board. This one goes all the way up to 600 volts. So basically, what it's going to do here is it's going to let you do 480 volt delta. So there's a difference between delta and Y. One of the reasons we asked the question from a panel board manufacturer. Circuit breakers don't all carry the same rating. So this one is only good for 480 277. This one can handle 480 delta, so Y and delta. You get a little bit higher amperage, 600 for a main breaker, 800 for a main lug, and the key here is you can go up to 225 amp branch circuit breakers. And that allows you to have, you can look at this chassis a little bit. I think the next picture is a little bit better. You can have your main breaker. We actually put a neutral. We got a couple of different designs in there, but a neutral in the middle here. Okay, but down here, you've got a chassis of black breakers, and that's just like this panel here, right here. But yet I've also got some of these larger breakers right above it. So it allows you to put two types of panel boards together into one. Good hybrid panel. Okay, and your power line 4 panels. This is the 4B. What does the B stand for? Breaker. Same voltages. This allows you to go all the way up to 1200 amps across the board. Okay, this is what the panel board looks like. You can see one of the differences between the smaller 1s and 2s and the larger power distribution 4 is that you can see it's resting on the ground. Now it's only 11 inches deep, so you can't set it in the middle of the room, and it's not necessarily designed to be a standalone piece of equipment, but you can rest it on the ground and basically bolt it to the wall to hold it up. Okay, 4Bs for breakers. Okay, this is an assortment of sizes. Let's see, to give you some concept in size, this breaker is that one there. Oh. I did. I accidentally. All right, so that one's that size. And you can see these go up to 2,500 amps. You can't see there. 1,200 amps for a panel board. Okay, 4F for fusible. Everything else is the same. It's just a matter of fusible switches versus circuit breakers. And you can see this one might be a 400 amp fusible switch. Fuses inherently are bigger than circuit breakers. So when you're talking a space savings design, a panel board or switchboard that has breakers may be half the size of one that has fusible switches, which is another reason why folks are all moving to circuit breakers instead of fusible switches in panel boards and switchboards as well. Okay, when you open the door, you can kind of see a little bit. These white things here are the fuses, and you actually got a little switch mechanism here on the side.
Is that you disconnect?
Yeah, should be here on the side here. Yep. Yep.
Now, when you are working on a piece of equipment like that, and to pull the fuse out, this is energizing board on one side at least.
Yes, if you asked us, how do I replace that fuse, we would tell you, you go upstream, like you mentioned before, to the main switchboard to isolate this completely, so you can get in there and grab onto that, onto those fuses. A lot of old-time electricians don't, they don't, I can do it, until it just, it only needs to happen badly once.
Arc flash.
You gotta remember that. The power line 4 panel boards, I showed you the B for breaker, the F for fusible. You can also hybrid and actually put both of them on the same chassis if you had a need for both. And everything is derived by what they call X space. I won't get into the specifics, but you've got a limited height of a panel board. 90-inch can is the largest you can do. And it's all driven by what they call X space, which is how many breakers can I fit physically in this thing for fusible switches. Okay, that was panel boards. Jumping into switchboards. Anything else before I jump into there?
I do have a question,
Yep.
related to 2014. What are you guys doing for the 1,000 volt rate? They moved the threshold from 600 to 1,000. How's it going to impact you? Maybe we'll talk in private about it after you finish.
Yep. Well, generally, I don't think it'll affect us in normal commercial distribution. However, one of the reasons I believe they did that is for the solar world. Solar arrays and solar, specifically if you get out to California, they're everywhere. And solar power is, it's much more cost effective for them to do a higher voltage, the way those things work. So they're pretty much standardized now on 1,000 volts.
So do you guys
DC.
Would you guys have a 1,000 volt DC disconnect switch now?
Yes. Yep. Probably in the last 5 years, we've come a long way. So if you looked at that, we've got everything 1,000 volt DC from, I guess, all the solar arrays, you combine them, and once you get to that first point, we can do 1,000 volt rated equipment. Inverters designed for solar, and then everything on the AC side as well, which a lot of that we've already had for a while. Yep. And now you can actually buy a switchboard, 1,000 volt DC switchboard. If you wanted to use that as your combiner and bring 20 arrays into one switchboard with a bunch of breakers and then upstream, we've got that product.
Do you do the AC 1,500 volt DC or no? I think IEC goes to 1,500 volt.
I don't think we do. I think we took a big step to 1,000, and that's about where we're stopping. They may do things in England or in Europe that are a little different, but we may not see it here. But leading into your, I'm going to throw an asterisk on your question. It wouldn't shock me if we move up to Canadian distribution levels, which are what, 550 volts. Wouldn't shock me because everything we do now is already rated for 600 volts. So it wouldn't shock me if they expand that up and we start seeing some odd voltages creeping in a little higher. Think about higher voltages. What do you know? When you get a utility bill, certain percentage of whatever that utility bill is going to be losses. Means you're paying for money, you're paying utility for energy, you're not using, you're throwing it away. Losses are tied to impedance, resistance, and one of the things you can do with a higher voltage is you can get lower losses. And so rather than using 90% of the energy you're paying for, maybe you can use 94% of the energy you're paying for, or something like that. And money guys, energy directors, these guys are all looking at things like that, and how to squeeze every dime out of a design or a facility. So a lot of the stuff for switchboards is going to be the same. But pointing out the big difference here. Panel boards, you're limited to 1200 amps. Okay, switchboards go all the way up to 6000 amps. So, that's the big distinction there. The panel board I mentioned hangs on the wall or sits on the floor and is bolted to the wall. The switchboard is designed to be a entirely standalone piece of framework. It's got supports on the corners, covers over all the devices, and it's got the ability to have main horizontal cross bus. And what that means, you can connect multiple structures of switchboards together without having to do any cabling between those structures. Because it's in a room, you can make it front or rear accessible. And because they're just inherent to the way the switchboard is designed, here's a typical one, is you have the ability to put certain metering compartments in there as well. I think I got a better picture. Here's a better picture. So here's normal distribution, and you may have a main device, and we've got two other things here called customer metering and utility metering. And I'll touch on those here in a second. So from the main device, you're going to get the same options of having main lug or a fusible switch. One other thing you can get is actually a fusible bolted pressure switch. And from your circuit breakers, you can get a regular circuit breaker or an insulated case or an air power circuit breaker. And I'll touch on a couple of the differences here. So from the molded case side, you can go all the way up to 2500 amp in a switchboard. Now, you can see the size of this breaker right here. That operating handle is huge. Oh, look at this.
We got one donated.
Oh, look at that.
So here's
Who gave you that one? That's nice.
From Allianz.
Okay.
Grabbed on them and they donated to us.
Sure.
I don't know if you guys wanna. Is it Cutler hammer? Is it?
Yep, that's ours. Yep.
I don't know if you guys can see it here.
Yep.
You look at it. That's a circuit breaker, 4000 amp, I believe.
Oh, that would be 32 probably.
32. Yeah.
Yep.
Okay.
Yep.
So I thought that would be great too.
Yeah, no, when we come up, I'll make sure to cut through and spend some time looking at that. But so your molded case breakers, which is this type, molded case being it's all plastic on the outside, can go up to 2500 amps. But the 2500 amps have this big operating handle, and they're very tough to operate. You have to you have to put like an extension on that handle to get that thing to move, just because there's the springs in there. Make it very difficult. All manually operated. From a fusible switch, in a switchboard, you've got an option of a regular fusible switch, which is a handle disconnect that goes up to 1200 amps, or something they call a bolted pressure switch, which it actually goes up to 5000 amps now on a bolted pressure switch. And in a bolted pressure switch, this is the operating handle right here. Okay, so from the front of the switchboard, it's like a left to right swing action. And there's springs in there that snap shut and open and close the switch. You can get a couple options. You can get manually operated or electrically operated. Manually operated would be a standard spring operated type device. Electrically operated is a different manufactured process, and then they put a trip mechanism in there so you can trip the springs and the switch open. Now, why would that be a benefit? Talk about service entrance, which will come on. Service entrance is going to require ground fault. Ground fault protection is going to require the main device to trip. So if you get in a case where your service entrance and you need ground fault, you immediately jump up to an electrically operated device if you're looking at a fusible switch. Okay, and this breaker over here, the Magnum SB or the Magnum DS, under circuit breakers, I said you got molded case, insulated case, or air power circuit breaker. Insulated case and air power circuit breaker are pretty darn close to the same breaker. For us, the Magnum SB is insulated case, the Magnum DS is air power. And the difference being same breaker, different colored faceplate on it. Difference between Magnum DS breaker and an air power circuit breaker is designed to go in switchgear. The big difference on that is you can have a 30 cycle time delay before any tripping action is required in switchgear. Okay, so when we talked about selective coordination and being able to get the downstream breaker to trip first, if you can put a time delay in your main breaker or a time delay in your feeder breaker, so that breaker, when it sees a fault current, doesn't trip, it can sit there for 30 cycles while 40,000 amps is flowing through it in a fault condition, and it'll sit there and wait until something downstream trips. If the downstream equipment melted into a pile of copper and nothing tripped, then it'll do its job. But it always lets the downstream stuff get first crack at it. And that's the Magnum DS, which is for switch gear. The Magnum SB, rather than a 30 cycle time delay, you have a fixed instantaneous, which basically means you're really like a 3 cycle breaker. 30 cycle for switch gear, 3 cycle for switch board. Same standards as these breakers. There is some time delay in there, but it's not unlimited. One of the differences between a molded case and an insulated case for air power is this breaker here is, when you look at it, you can see it's pretty big. It's all individual parts. You've got springs and washers and bolts and all this stuff on the inside. You can take this breaker, you can put it on the shelf, you can break it down, clean it up, sandblast some stuff, put it all back together, replace a part here and there that's needed, and get that breaker to last for years, 50 years, 60 years, what have you. Generally speaking, electrical equipment, although nobody will actually publish an expiration date, generally you want to look at about 30 years before your equipment is ready to be replaced. Anything extra is usually borrowed time. Sometimes 35 is good. Other times you get a dirty environment or an outdoor location where it's hot, something dusty, or something where you're running a lot of current through it at all times. Maybe you only get 20, 25 years of life out of that equipment. So maintenance is one of the good benefits of these breakers. The other benefit and why we use these as main breakers a lot is you have the ability to have an electrical operation. Okay, so open and closing the circuit breaker here is a physical action of moving this handle up and down. This breaker, it's a physical action with a couple of buttons on here, but there's a spring in here. So I can pump this handle here. Okay, pump that a couple times and charge the spring, and that gives me an open, close, open push buttons I can hit to do those. And by that time the spring's uncharged, and that's it. However, I can also put a little motor operator inside here that can automatically charge the spring, and that's what makes the breaker electrically operated. So when I open the breaker, the motor operator charges the spring. I can close the breaker and open and close it. And every time I'm continually charging the spring, So I don't need to be in front of that breaker. I can stand at a push button station on this wall and open and close that breaker over there. Now, why would this be handy? Think about safety. Okay, an arc flash. If you're out standing in front of a piece of switchgear, open and closing a breaker, it's a dangerous situation, and it may say you need to wear the full protective suit with the helmet, the face shield, and everything. Versus here, I'm now 30 feet away, and I'm out of the blast zone. Maybe I'm even around the corner, and they can do it in whatever means that calls for, but it's going to be less. So the main devices in the switchboard are usually individually mounted, especially anything over 1200 amps. And they'll just put her in the structure with some devices above it. But we could do it in a chassis up to 1200 amps. Okay, I mentioned the utility metering compartment. Utility is bringing 480 volts to your commercial building. Nowadays, more often than not, they're going to put some kind of little cabinet outside. And they're going to connect their metering equipment outside by that cabinet. Once those cables come through the building wall into your switchboard, that's all your power. Sometimes they actually put the metering equipment inside the switchboard. So here's the switchboard where we've got a metering compartment here. Now this is really what it is. It's owned and designed by, in our area, Excel, and it's a place for them to put their CTs for metering. So visually, this is what we're looking at. We've got two types of CTs: a donut type, where your bus bar, or the donut basically goes around the bus bar, or the bar type, where we make A and B phase, or A phase with a big hole in it, and bolts on both sides, and the utility comes in, and they bolt a bar CT on each end of there to complete the circuit. Once they get their meters, their CTs hooked up, then it just leads out to wherever their watt-hour meter needs to be located. Get two kind of metering compartments. There's a hot sequence and a cold sequence. And the hot sequence is when the compartment is always hot. In other words, you're bringing in your cables from the utility to your switchboard, then you got the metering, and then your main breaker that feeds more switchboard structures or the rest of your building. This is how they do it here. Some folks do it cold sequence, which means if I open my main device, my utility compartment is dead. Now the other thing, utility metering compartments are all used by the utility. None of that information is available for the owner until you get the utility bill. When you get the utility bill, and you're a big commercial building, maybe you're paying $5,000 a month for electricity. You look at their bill, you say, okay, $5,000 bucks. I got no way to prove you're right or wrong. Here you go. So what most folks do now is they put on their own metering called customer or user metering. And in the same switchboard above the main breaker, we'll make about a 15-inch high compartment with the customer's metering equipment behind some kind of hinged door. Now what that allows them to do is you can always verify the utility bill with whatever billing parameters you're getting billed at. Sometimes it's strictly kW kilowatt hours. Sometimes they put a demand charge. They want to see when your peak usage is. And sometimes they'll put a power factor penalty charge. And all these can be factors in the utility bill. So from an owner's standpoint, or as an engineer talking to an owner, you have to understand what they're getting billed for as part of your design of being able to save them energy. And the only way you can manage your energy use is to monitor your energy use. So we always say you should always have a meter at your point of service entrance. In the back of that switchboard, we actually put the CTs around the bus, so this is usually out of view in the switchboard, and so your A, B, and C will come right through these CTs. which feed into the meter. And you've got a few different flavors of meters. I've kind of broken them down into three options from what a customer can expect. The most basic is that of a what I'll call a digital ammeter and voltmeter. It's a meter with a nice little display, lets you see amps, lets you see volts, gives you a few other things to step through in there, and that's a basic walk up to the meter and read it kind of information. We can take that same thing and make it Ethernet capable. And the trend of the industry is everything's going to Ethernet communication. So we can take this meter. We've got a communication card that slides in the back. You assign it an IP address, just like any other device on the network. Plug a LAN cable right into the back of the meter. The meter itself has a built-in web browser, a built-in web server. So from any PC that has authorization through this backbone, or through your inside your building, if there's a firewall or something, you type in the IP address 199.66.85 or whatever, and boom, the internal web page pops up. And they're pretty good right now, and you can have graphs, and you can have waveforms, and you can have trends from today to 6 months ago to a year ago to look at your energy usage and how things are tracked. Now, a lot of times, the other things, you can get simple fact like power factor, bars, percent harmonic distortion, a lot of that stuff comes with it nowadays. Pretty standard as far as an energy meter. So the two basic ones are energy meters. You can get energy meter non-communicating, energy meter communicating, or the upper level, which I'll call a power quality meter. And a power quality meter has the ability, more than likely you'll get the same Ethernet connectivity, monitoring your voltage, current, and all the values that go with that. But you also get the ability to have a waveform view. And this particular one, and I can't see it very good, but it comes in two pieces. This meter itself is about like a shoebox, so it's much bigger. And the display then can be mounted anywhere. And you can kind of see on the display a little bit. Same information that's going to be in the web server, but you can see an actual waveform. And in the case where you have a fault that occurs, your circuit breaker tripped, you're trying to go back and look what happened, you can pull up that fault condition, pull up 30 cycles before and 30 cycles after your tripping event, and you can literally look at the waveform, see what happened, see when it spiked, see when it tripped, and see when it turned off. A couple of these meters or some other information, great use for triage, I guess is the word, to try and figure out what happened, like at the airport. They had a tripping incident, shut down the airport. It's pretty major for about a day, a half day and a day. They had no meters. They had no clue how to do this. They go, well, it tripped, and then you got some veterans who've been around for 40 years to go out there and try and pick through the pieces to figure out what happened. Fine and dandy if those guys exist, and even into the best condition, they're guessing on what happened. So today, and one of the things they're going back retroactively and doing is adding meters around the airport in select locations. So if an event does happen, they've got some means to pull up some data and go, okay, well, this tripped first, then this tripped, so we know the fault started here and propagated to here. And you put those pieces together to figure out what happened. If you figure out what happened, you've probably got a decent chance to prevent it from happening again. So all these meters really are, I'm going to call them invaluable tools on how to run a facility.
Todd, I don't know if you know, in 2014, there's a major change where they will allow you to size the lighting system based on energy code, not based on the code, electricity code. If you can prove that your lighting system is what you say it is. So that might come handy, for example, when you for a commercial building, we use 3.5 volt amp per square foot to size the lighting load. if you're using LEDs, you can get away with 1 volt amp or less than 1 volt amp to meet the energy code. But why do we need a bigger panel thing? So they're allowing you in 2011 to size based on energy code, which is a major. I believe it's going to be a major thing.
Yeah.
So you might see smaller panels, lighting panels. So I wonder
We,
if these but you need a way of verifying it. I was wondering if these meters will be a way of verifying that yes, my load is what I say it is.
Well, it is, guys. I'm going to throw out an example. There's a major manufacturer in Austin, Minnesota, that built a new corporate building. And when they started engineering it, they sized everything, I think, for regular lighting. I don't know, not incandescent, but fluorescent or whatever that level is. And they went through the design. They got a nice 3,000 amp switchboard in there for their facility. Figured they'd have, I think they were thinking somewhere like 800 amps for the load. I think they had 4 225 amp breakers specifically for lighting. And they added this meter. They separated 4 loads, like wings of the building or what have you. So they had 4 of these meters and a switchboard looking at all 4 loads, expecting to get, 150 to 200 amps, I think, per little section. And when they actually got it up and running, they ended up going with LED lights, and they were barely getting anything on the meter. I mean, they're showing like 50 amps, 30 amps, and they got this huge service, and they're going, well, I guess we only needed 1,200 to run this building, and instead they got a 3,000. But they're able to prove that. And so now they know when we add this wing on here in the future, which they're going to do, they don't have to get another service, which may cost you $100,000 to get Excel to come in and dig in the service for you. They could just tap off what they got existing because they have a continuous understanding of their capacity in their board. Information is power. On your switchboards, your feeder breakers, you can actually stack them. I mentioned 1,200 amps is a base you can put on a chassis feeder board, but you can put individually stacked feeder breakers just like a main breaker, which takes the limitation out of it. SPD devices, most important location is at your service entrance point. If that's a switchboard, we kind of mount it like this, where we'll put a little circuit breaker in here to act as a disconnect right into the side of the unit. One of the other things when we talk, the example I mentioned used those larger meters to monitor 4 different circuits they were looking at. A lot of times you're going to be more than that. You build an office tower and you're going to rent out the entire first floor to different retails, a Starbucks at one, a Subway at the other. You want to charge everybody for the energy that they're going to use. You might have a switchboard where you've got 12, 15 tenants that you want to sub-bill out of that switchboard. So all manufacturers have some type of devices. This happens to be ours, something that maybe snaps right on the bottom of a breaker. Something like this.
Is it retrofit?
It is. It could be, yeah. Or this one actually, it's designed, you can actually bolt it into the sidewall. So if you got enough space in there, you can bolt it on the side, just run your cables through there. There's all kinds of different options available, and these are continuing to change in the industry today. Over the last 5 years, you've seen a lot of swing in these. And it's a means where you can gather your energy data for different tenants, bring it into some master piece of equipment to be able to gather and sub-bill all the tenants the energy use. Anything you can build as a building owner, anything you can bill out to tenants comes right off your plate.
Do they get work? They can talk to each other, or you have to individually read them?
These ones, yeah, there's not even a display on these ones. So this is an option where you would daisy chain your 12 of them together in a switchboard. Then at the front of the switchboard, you could put one display where you can toggle through and scroll through your different ones if you wanted to do it that way, manually read how much energy usage. Or you could then put an Ethernet card in there, take it somewhere, and so the building manager can sit at his desk, pull up the same information, and maybe even be able to generate some. We had a program we called eBill, where it sucked the data and you hit the button and it printed out little bills to customers. So there's all kinds of that stuff available. Okay, going back to our standard distribution here, here's the building wall here. We've got your utility metering either outside the wall or inside the wall. But this point right here, I mentioned this early, is your main service disconnect or service entrance point. So some of this may be familiar, but service entrance equipment has to be considered separate from all the rest of your equipment. And why is that? Primarily the way I can figure is when your building's on fire and the firemen come into your building, they need to know what equipment do I turn off to shut off the electricity. How do I isolate my building's power? So that piece of equipment needs to have a service entrance label factory attached to the panel. So that's a little sticker that says service entrance equipment. And we have to do it in the plant. We can't ship a sticker out for somebody to do in the field. UL does not authorize it. NEC does not authorize it. For disconnects, if you've got a main circuit breaker, great. If you've got a main lug only switchboard, you're limited to a maximum of 6 feeder breakers or 6 disconnects before you need to add a circuit breaker. That's probably the most that can be expected to be reasonably turned off, I guess, in a reasonable amount of time to isolate your building. We also, when we make a switchboard that is service entrance rated, we put a disconnectable electrical bond in the panel between the neutral and the ground. It's basically just a copper bus bar that would bolt in there between the 2 pieces of equipment, ground and neutral.
That's the main bonding jump.
Yep. Yep. That's it. So service entrance requires the sticker, the bonding jumper, and the last thing that's the important one to remember is ground fault protection on anything 1,000 amps or more on a 480 277 volt system. So with that said, we need to have this information as a manufacturer, when we build this equipment. You can have a 6 disconnect rule, which you can get away with, no more than 6, or you can have a main breaker, and both can be service entrance type equipment. A couple things on ground fault. Okay, ground fault protection. One of the reasons NEC requires this is because ground faults generally have a very high resistance. So when you get a high resistance, you're going to get a very low current. So you get a fault condition where you've got a 2,000 amp breaker on a typical phase C to ground fault, maybe some of the insulation rubbed off of a wire, and it's shooting to one of the conduits or something else, and it's got to the point where you got 300 amps leaking to ground. This 2,000 amp breaker will never trip under that ground fault. Okay, and that's going to continue to ground and arc. Sparks are flying, and eventually something, either it's going to burn itself out, which you're hoping, or more likely some of the non-conducting materials are going to catch on fire, and you're going to start insulation on fire or some other part of your building, and that's where your incident's going to start. So to address that, they've got specific ground fault protection. 2 types. It could be a ground fault embedded in the trip unit or a ground fault relay that is separate. And the two kinds you can do with that is zero sequence or residual. So zero sequence basically is one CT around all the phases in the neutral. Residual has individual CTs on each phase, and then it sums up the total. So kind of give you a better look at that. Okay, in the back of my switchboard, I've got A, B, and C, and neutral. And what current flows on neutral? Anything unbalanced. So if you've got all three-phase loads, you shouldn't see any current on neutral. If you've got a bunch of single-phase loads, normal buildings like this have almost all single-phase loads. Anything unbalanced, where you plug it into coming more off A and less off C, is going to flow into neutral. So you always need to monitor the current in the neutral as well as your A, B, and C. And at any given time, remember your A, B, and C is 360 degrees in a cycle, and A, B, and C are all offset by 120 degrees, three phases. Everything's shifted into a thirds. So in a three-phase system, at any given snapshot in time, your current should be zero because there's as much positive as negative in any given snapshot in time, summing all the phases in the neutral together. If that's the case, 0 amps come out of your CT, ground fault relay doesn't see anything. In the case of a ground, your CT is going to be imbalanced. It's not seeing this flowing here. You're going to have some imbalance coming out of here when you hit the preset level that you dialed into there. Maybe you dialed in 300 amps. When it sees a 300 amp discrepancy, then your relay will activate a shunt trip to actually trip off your main device. Now, residual does a little bit different. You've got individual CTs on your three phases and your ground. All four of those pieces of data go into the ground fault relay, which does the adding and subtracting to make sure they should all equal zero. And this is the way solid-state trip units and circuit breakers are made. So the solid-state trip unit, which is the printed circuit board and the breaker, looks at your A, B, and C. Because you don't run a neutral through a breaker usually, you've got a separate loose CT that you connect and wire in to this trip unit. Okay, so that's taken an input as the 4CT. That again, we'll look at it. If everything's not zero, it's going to initiate a trip signal, hit the trip bar, and trip the breaker. Switchboard construction, basically the concept on a switchboard is that you've got a bunch of building blocks that you can snap together in every way you like. Multiple structures, 2, 3, 4, 10, 11, 12 structures that can all be bolted together with common bus to create one big distribution point. You can have, in addition to your mains and your feeders, you can have cable pull sections which isolate your utility incoming area and keeps all that separate. And how a switchboard is made is we just take all these individual building blocks from a manufacturer's side and stack them together. I don't think you guys probably haven't talked about busway yet. Next project. But one of the means, everything I've talked about to this point has been cable. Cable is the way to distribute power from one piece of equipment to another piece of equipment. A second alternative method is called busway. Busway is phase bars. And actually, let me just look at this next picture here. Okay, this is busway. And you've got A, B, and C here. So inside that busway, you've got 3 bus bars. One for A, one for B, one for C. You might have one for neutral, you might have one for ground. And all these bus bars are insulated, wrapped together, sandwich packed, and then aluminum around that. So you could have 3,000 amps of busway that is this size. 3,000 amps of cable might be, a bundle of stuff like this. So you can save a lot of size, you can save a lot of install cost, because to install busway could be done in a fraction of the time. And the other reason folks use busway is, for example, on a high rise where you need to get power all the way up, maybe you're going to the 20th floor. You think about what happens if you run cable from the basement to the 20th floor. What's the number one thing you're going to run into? What's the problem? Voltage drop. Each inch of cable is going to lower the voltage just a little bit more until you get up to the top. Busway has a fraction of the voltage drop that cable will have, because a busway is really a continuous bus bar running all the way from the floor to the top. When this busway comes into a piece of equipment such as a switchboard, it takes that sandwich busway coming in and spreads the phases out into the fingers that you see here, A, B, and C, which then can connect to your actual copper bus bars in your switchboard. So here's your busway into the top, coming in, spreading out into a flange situation, which then feed your main. And I'd say busway is very common in long runs. If you've got a big campus, a big lab building, like a big warehouse, and you got to go from one side to the other, busway is going to save you a ton of money in your design from the installation standpoint, not having to worry about voltage drop standpoint. The same thing applies when you're going vertically. And when you're going vertically, busway actually has the option of being able to tap off every floor. If you want to tap off every floor with a circuit breaker, you can put a circuit breaker every floor, and it's a great distribution method. But I won't get ahead of your design. That's it for the panel board and switchboard presentation. If you guys have seen this one, see, it's got it all tabbed nicely and everything.
Can you just grab that book?
Yeah.
Because I'll have one book. This is the.
Yeah. This is the 15th edition consulting application guide, originally designed by Westinghouse, now carried on with Eaton. You guys heard the name Westinghouse? That's, most people don't know what Eaton is. Maybe now they're starting to learn a little bit, but George Westinghouse, back in the, 100 years ago almost, was in on the development, I'll call it the development of, how do you create electricity? So AC, DC, all that discussion was had 100 years ago, and Westinghouse was involved with founding this company that came up with this thing called a circuit breaker. And Westinghouse Electric, all the way up until 1994, was one of the predominant engineering companies and equipment providers in the United States and the world, for that matter. And in 1994, Eaton actually went in and purchased the Westinghouse distribution and control unit, because Westinghouse, I think, made the mistake of getting into the TV industry. I think they bought David Letterman and a couple other, they bought networks, and were losing their shorts, so they had to sell off, and Eaton bought the best piece out of that, which is the distribution and control part that we've been talking about today. Since 1994, it's all been Eaton. Eaton is the name of the company. We make, our company slogan is powering systems worldwide. And so everything we do has to do with power. So we've got divisions that deal with trucks and autos. So when you're talking trucks, you see, when you see a bus driving down with a hybrid system on it, more than likely that came from us. We developed ways to take hydraulics, save the energy, and reuse it. When you hit the brakes generate heat. heat can be saved, used in hydraulics, and used to save energy. So we're in all that from the automotive and the car standpoint. From we got an aerospace division that we vastly lead our competition on distributing hydraulics. I believe it's 5,000 psi. Have to double check that, but we're able to make very solid, small, lightweight tubes that control all the aeronautics on a plane. So when the guy sitting at the pilot, I guess they call those guys, sitting at the front of the plane is steering, he just makes a little flick of the switch, and the tail rudder moves left and right. And we could, because this design we make is a very high PSI design, highly engineered. It allows the plane to save tons of weight. Instead of big pipes, you get really small pipes. And every ton of weight on a plane, you can think about it, that's all fuel. The number one expense is fuel.
Is there a lot of fail-safe on that sort of thing because it's under such high pressure?
Yeah, I'm going to say yeah. I'm guessing there it's a redundant, 100% redundant. If it was my plane, I would design it as 100% redundant.
5,000 PSI,
Yeah, yep. And we do, so everything we do is tied to powering businesses, how to make it more safe, how to make things more energy efficient. So from my standpoint, which is Eaton Electrical, we've got all the distribution gear that we're talking about here. We've got PowerWare, which is UPS. And UPS is basically battery-powered backup. So if the power fails, I can run my computers for, I guess, however long as my batteries last. If you get a big data center, those batteries may last an hour or two. If you get at a place like our office, if the power goes out, which just happened a couple weeks ago, we have a half hour to an hour to finish what we're doing, shut down our computers before the batteries run out. We also have a generator company. So there's three legs: utility power, which we covered today; UPS, which is battery backup power, which we have PowerWare does that; and the third leg is generator power. Those are really the three sources of power that you're going to have in your system. And we have we started a joint venture about 10 years ago with Caterpillar called CAT-ISO, but it's a generator paralleling switchgear manufacturer. We make the switchgear and the breakers. Caterpillar makes the generator and the generator enclosure controls, and we put them together in a partnership, each doing what we do best to basically complete the package. And Chad, I don't know if you knew this, but a year ago we closed the deal. Eaton purchased Cooper Industries. And Cooper Industries, Cooper Power, yep, that's one of them. Cooper Industries makes Cooper Busman fuses, Cooper Power Systems, which pad mount transformers, stuff like that. All the Krauss-Heinz things where they're like the world leaders in explosion-proof type stuff. If you go into a mine, you're going to see Krauss-Heinz stuff. All kinds of connectors. If you go to a solar array out in California, everything from the panel up to the gear is all the Cooper stuff. So when I said before, once you give us the power, we can do it upstream. And now that we have Cooper, we're still learning how we fit together. But basically, they added all the downstream connectors and stuff. And now we have all the upstream because Cooper Power is a large presence in the utility market. So they're doing things like when you climb the utility pole, there's little switches and stuff up there. In utility switch yards, there's a lot of equipment. They do all that stuff that we never did.
So they follow the for Boston and all that?
I'm going to guess yes. Chad mentioned Cutler Hammer. I'm Eaton, but we make Cutler Hammer products. So it's going to now be Eaton with Cooper Busman products or Cooper Power products. That may change because it's only been a year and there's two pretty large companies. We were 15 billion, they were 5 billion, give or take. So now we're going to be about 20 billion, and it takes, I'm going to guess it's probably a 3-year process before you integrate that, before they figure out, well, does it make sense to change names or what have you? But as of now, it's two separate entities, two separate relations and channels to the customer.
So was yours, you were based out of Glendale Heights down in Chicago?
Yes, you been down there?
I used to live there.
Okay.
Yeah, I worked at, or I was.
Yeah.
Yes. You know the golf course right there in Glendale Heights, the city golf course?
I don't. And actually, I left, I worked there when the office was in Westmont. And right around the time I left, they were moving out to where they were combining the sales office, panelboard, switchboard manufacturing, and motor control center manufacturing all under one building.
Okay.
And I left right before they transferred that over.
Okay, yeah, that's where I finished college for some, so I finished out there, so.
Okay.
I worked at the golf course on Glendale Heights, so.
Okay. Well, you hit my sweet spot. Definitely a golfer. Um, any other questions, I guess? Take any open forums about, I'm a manufacturer here and I'm talking impartially, so as you start to get into your
Yeah,
next
remember, we
career.
have you in the industrial project too? I can't remember. You come from the
I haven't
industrial?
yet.
Let's talk about Shell too. You
Okay.
just talk about the buses and MCCs and.
Okay.
Okay, I think that's great for what you learned. Thank you.
Okay. Sure.
Thank you. You guys have any question for Todd? Great presentation. You will also see it on YouTube too.
Mm.
You missed a whole lot.
YouTube. Okay. Oh, I never quite showed you this book there. I took it out, but the Consulting Application Guide's been around about since the 70s when the first one came out. And it's an Eaton exclusive in the industry. And it's for the folks who use it, they'll live and die by it.
I'm one of them.
Yeah, I can't last 3 years because I end up ripping all the pages and folding the corners and stuff on it. We can't make it any thicker because the publisher, the book guys, said we can't fit any more pages in there, so we have to keep thinning it out. But it's a great tool. It's got a chapter at the beginning for, I'm going to call it general electrical stuff. So if you want to learn about UPS in 2 pages, this is a way to do it. Ground fault protection in 3 pages, it's in here. And it's got all your different applications, like in 40, 50 pages, I think, in there. Then we've got individual chapters on some power management techniques. We've got a section on substations and switchgear. And then we've got sections on low voltage distribution equipment, everything 600 volts and less, panel versus switchboards we talked about today. And sections on circuit breakers, control products, and then the power quality stuff at the end. But it's
Do you guys do your switch gear or anything like that, built in with like IR windows or anything too?
yep, all that's an option.
Okay.
IR windows 10 years ago, I wouldn't even hardly know, nobody really asked about it. And today, it's asked about less in commercial installations, but when you get to industrial, it's quite common. You might be 50 to 75% of folks are gonna, if they don't get it, they're at least gonna ask about it. That's gonna tie back into safety because, and uptime. People, you got to maintenance on the equipment. Things, as cables are connected to a lug, heat, which is caused by current flowing through there, your load's gonna get larger and smaller, which means your cable's gonna extract and expand and contract, and it's gradually gonna loosen up over time. So you're gonna have to go in there and torque it. One of the things you do is you take a heat scan piece of equipment or a heat scan camera, and in the old days, you might take the back cover off where you're exposed to the 480, and you can take camera shots and check your temperatures of all your terminations and stuff. Nowadays, we put the low infrared window right bolted into the back pan, so you can take the camera outside of the switchboard, hold it up to the window, take a picture, move down to the next window, take your picture, and move on. And you can keep a continuous recording, so you can look at every 6 months from this spot. I've been at 130, 130, 130. Now I'm at 145. I better take a look at what's going on inside.
So in two, for like your power quality meters, just that they can communicate wirelessly, that is develop their own software as far as like collecting all that data, or do you work with somebody who kind of sets up something like that for you?
Well, I said they connect on the Ethernet.
Okay.
Okay, so traditionally I'm going to say they do, they're hardwired, just like your, like you plug it into the site, your
Yeah.
Cat 5.
Yeah.
We do have a wireless option for not the power quality meter because those waveforms are big chunks of data. But for the energy meter, we do have a wireless option. So you set that up there, and it takes no software. The industry from the 70s or 80s, I should say, till today, has gone from customized, individualized software. It always got outdated. The guy who put it on his computer left. Nobody knows how to use it. We've kind of shifted to software free. We'll have software available if you need it.
Yeah.
Okay, if you've got 100 meters, you can't just rely on looking at each individual meter by itself. You want to get some software that gathers all 100 meters, lays it out in a nice spreadsheet or some easy format. And we do have that available. We keep trying to make it simpler and simpler so it doesn't become obsolete when the one guy who's trained on it leaves the company. Okay?
Well, thank you, Todd.
All right.
Awesome. Thank you.
Thanks, guys.
Thank you. Great presentation. That's awesome.
And I've got some cards here. When you guys land at your chosen destination, you can feel free to